Welcome to Green Chemistry, thermodynamic constraint-based design of zero-waste chemical networks. In this lesson, we will build intuition, equations, and visual tools to design networks that minimize waste while obeying physics. We will explore it chemically, mathematically, statistically, and graphically. Here is our roadmap. 1. Chemical intuition with a reaction network diagram. 2. The math with mass balance and thermodynamics. 3. Optimization to enforce zero waste. 4. Uncertainty and statistics to test robustness. 5. Graphics that help us see feasibility and design trade-offs. Let us begin with chemical intuition. Consider a simple network where feedstock A is converted to B, then to our desired product C. Sometimes, an undesired byproduct W appears. In a zero-waste design, we loop byproduct W back into the network so it is consumed or upgraded rather than discarded. We will visualize species as circles and reactions as arrows. Now, the math. At steady state, mass balance says SV equals 0, where S is the stoichiometric matrix and V is the vector of reaction fluxes. Thermodynamics connects reaction direction to free energy. A reaction's delta G equals delta G, not plus, are T times the natural log of Q, the reaction quotient. Feasible steady states must satisfy both mass balance and thermodynamic directionality. A powerful way to impose thermodynamics in networks is through chemical potentials. Let mu be the vector of species' chemical potentials. Then the reaction-free energy vector is S transpose times mu. For forward flux, Vi greater than 0, we require delta G, I less than 0. For reverse flux, delta G I greater than 0. This prevents impossible perpetual cycles and enforces energy dissipation. To design zero waste, we compose an optimization. Minimize waste generation subject to mass balance capacity bounds and thermodynamics. For example, minimize W transpose V, where W selects waste-producing reactions, subject to SV equals 0. Lower bounds less than or equal to V less than or equal to upper bounds, and the direction rule enforced via chemical potentials. Graphically, feasible fluxes form a polytope from mass balance and bounds. Thermodynamic constraints carve away directions that would increase free energy. We will draw a two-dimensional slice for intuition. The shaded polygon is mass balance feasible. Orange arrows show excluded directions by thermodynamics, and the green region shows the final feasible set. Let us ground this with hydrogen and oxygen. Hydrogen 2 plus half oxygen 2 goes to water. This reaction is strongly exergonic at room temperature, so delta G is negative. In a network, exergonic steps can drive the usage of byproducts, helping achieve zero waste design when coupled correctly. Data have uncertainty. Standard free energies are estimated with error bars. We can propagate uncertainty by sampling delta G naught, computing delta G under likely concentrations, and then estimating the probability a reaction is exergonic. Let us visualize a synthetic sampling of delta G values with a histogram and a 95% interval. Let us return to our earlier network and show a simple design target: zero waste. We penalize the waste reaction flux and encourage recycle. We will visually code the fluxes as arrow thicknesses and adjust them to reduce waste while keeping product formation and thermodynamic feasibility. To summarize, we combine mass balance with thermodynamic potentials to ensure only energy-dissipating fluxes. We then optimize to minimize waste, often by elevating recycle pathways and coupling with exergonic reactions like hydrogen to water formation. Uncertainty analysis checks robustness of the design across plausible data variation. Graphical tools make feasibility and trade-offs crystal clear. Green chemistry thrives on physics-aware design. Thermodynamic constraint-based methods give you a rigorous, visual, and quantitative path to zero-waste networks. Thank you for learning with us.